Okay, for section 2.4, we're gonna be graphing a function rule. So our essential understanding here, I'm gonna go ahead and read this, is that the set of all solutions of an equation forms the equation's graph. A graph may include solutions that do not appear in a table. A real-world graph should only show points that make sense in the given situation. The important thing here, and what they're trying to tell you, is we want to graph points and choose those points that make sense. Okay, so what that means is I don't want you to graph numbers that are way out of range. We want them to make sense to what you're trying to show. So I don't want to see x at, remember this line goes on forever. So here if you look at this continuous line, this goes on forever. I don't want to see at x equals 1,000,000. That does not make any sense. We want to find something that is within a certain range. So here you can see how this is within a certain range, and it shows kind of what's going on. And that's what you want to do for this section. So we'll be talking about continuous graphs and discrete graphs, and then finding what's a reasonable set of numbers we can use to show the graphs. Let's go on to the first example. Okay, so for problem 1, we're going to be graphing a function rule. So what is the graph of the function rule y equals -2x plus 1? So they want you to graph this equation. So the first step we want to do is we want to come up with a table. So I'm just going to go ahead and show you right here. Step 1 is to make a table of the values. So what it comes down to is we need to find a set of values that are reasonable. So on this example, I would want to use maybe a little bit of a negative and some positive numbers for x, because that would fit a more reasonable set of values. I don't want to go to x equals -20. I don't want some number way over here for x equal to -20. That doesn't make any sense. I don't want it to be way over here where x equals 50. That's not reasonable. We want to just choose a few points to show what's going on with the equation. So anyways, we're going to go ahead and plug in each value. So for x of -1, that means I'm going to go ahead and plug in -1 for x right there. So if I do that, I'm going to have y is going to equal to -2 times -1 plus 1, and then I will solve for that and get the point. So -2 times -1 is a +2. 2 plus 1 is 3. And so my point is -1 and 3. Now, I will repeat the process, but I don't want to waste time on this. I just want to quickly show you how this is going to work. And so I want to go ahead and just go straight to the equation itself. Okay, so here's the graph, and here are the points. So once you have your points and you've plugged in every value for x for a reasonable domain here, let's go ahead now and plot the points because we want to graph it. So our graph would be this right here. And if you notice, I use this range because it kind of shows me all the different points. So we know this is going to be linear. The points, we plot them, and here are the 4 points, and then we graph it. So again, it's all about finding reasonable points to show your graph. Let's go on to problem 2. Okay, on problem 2, we're graphing a real-world function rule. So this is the same thing we did as problem number 1, except it's more of a real-world situation. The function rule w equals 146c plus 30,000 represents the total weight in pounds of a concrete mixer truck that carries c cubic feet of concrete. If the capacity of the truck is about 200 feet, what is a reasonable graph of the function rule? Okay, so a few things here. They're asking for a reasonable amount of values that would work for this graph. Okay, what's important here is the equation. Okay, and we are looking at up to 200 pounds of capacity. So this 200 pounds is very important because this is going to give us a reasonable amount of a domain for a range. So what does that mean? So if I were to kind of look at values of x, and I'm just going to make this a little bit sloppy, but if I have a reasonable amount of x and y here, so here's my x. Okay, my x is going to be the letter of c, so x is going to really represent c, so that's going to be the c value. And my y, well, that one's going to represent the value of w. Okay, for in this case, it's going to be the weight. All right, so what is a reasonable value that I can use for x? Well, the key is that they told us that the capacity of the truck is about 200 feet. That means that I would want to start from about 0 and then go down to about 200 feet. Now, would I want to use 1, 2, 3, 4, and then all the way to 200? That's not reasonable. So what we want to do is find something that is going to be reasonable. Okay, so what would be a reasonable value to get from zero all the way down, say, to 200? Well, to me, you want just a few points. So I would go like every 50. So I would go 0, 50, 100, 150, and then 200. There you have 1, 2, 3, 4, 5 points. Maybe that won't work. Maybe we want to be a little bit more, a couple more points. Maybe we can do 0, 25, 50, 75, 100, 125, 150, 175, and 200. That's not a lot of points, but you could see how this is a reasonable domain for the x, so that I can get a reasonable set of values for our range, for a y, and then now we can go ahead and graph it, and it gives me a pretty good representation. So that's what we're talking about being reasonable. So let me go ahead and show you what to use. So for this problem, we're going to use the following. I would use these points right here. So we are going to use C is our x value, so this is our x right here. W is our y, and our W, our weight, is 146C plus 30,000. So we're going to go ahead and use, in this example, we're going to use every 50. So we're jumping from 0 to 50 to 100, 150, and 200. 5 points is good enough. We plug in for 0 for C. So C is 0. We plug it into a formula, we get 30,000. So our point is going to be 0 and 30,000. And we do the same thing for the points of 50, 100, 150, and 200. So we can see how these are going to be our C values that we're plugging in for these right here. Okay? And now we get our values of our weights, and now we have a table that's going to work for us. Okay, so now we have a reasonable set of domain to make this equation work. Now we're going to need a table, a graph here to fit the table. So for our graph, okay, you have to first notice that what is our values of y. So again, I want to highlight that it starts at 30,000, it goes up to 59,000. So our values start very high. So you don't want to use 1, 2, 3, 4 for the values of our domain here. We don't want to use something that is too small. We want something that kind of jumps around. So we're going to be using in the thousands. So you could see how we would use something, say, on the 20,000 here, and then maybe 40,000, and it makes 60,000. Why up to 60,000? Because if you notice, on our values, these values go from 30,000 all the way to close to 60,000. So that would be a reasonable range. And now we can plot this and see what's going on. And as you can see, once we plot the values of 0 and 30,000 right here, and then the next one 50 and 37,300 and so forth, all the way to a last point of 200 and 59,200, you notice that we have a nice linear equation. But this works good. This is what you need to be able to do on the exams. You got to show a reasonable set of values that fit the scenario given for this particular real-world function rule. Okay. All right. Let's go on to the next problem, so you can see some more examples of this. Okay. For this last example, problem number 3, we're going to identify continuous and discrete graphs. We got to read a scenario and determine which of these following is it. Would this follow a graph of being continuous, or follow a graph of being discrete? And we got to justify our answers. So discrete means that there's going to be gaps. Continuous is something that is flowing, something that can be kind of solved within any particular point. So let's read this first problem. The amount of water W, so we're looking at water in gallons, is wadding pools depends on the amount of time T in minutes. The wadding pool has been filling as related by the function rule of W equals 3T. So we are given two options and we got to decide, is this a continuous or discrete? So our two options are the following. For A, you have a discrete function that has, so there are gaps in between these points. Now, the graph is discrete because the time is measured in minutes. So what they're telling you here on this first example is that this would be selected if you're looking at jumping every minute. Okay? Now, on the second example, B, you see the same points, but now you have a continuous line. And the graph is continuous because you can have any amount of water. So the question is, which of the two do you choose? Do you choose A, being discrete, or do you choose B, being continuous? Okay, because water can be measured at any set of volume at any point, this would be our answer. It would be B. Water can be measured at any point. It doesn't have to be measured every minute. Okay, so that means that if you're looking at this scenario and you were to graph this, this would be a continuous, because the water continually flows down the pool. So it won't. So that would fit under the scenario of being a continuous graph. All right, let's move on to the second one. The cost C in dollars for baseball ticket depends on the number N of tickets bought, as related by the function rule C equals 16N. So again, we have two options. In this A, we have discrete. You can only have a whole number of tickets. So you could see how each value of the ticket can only be discrete because you're selling them only as complete wholes. Or is it continuous? You can purchase any partial ticket. So that means that you are allowed to buy a partial of a ticket. So the question is, which of these two are you going to choose? All right, in this scenario, you're going to have to choose that this is a discrete function. So the answer would be A. Why discrete? Because when you purchase a ticket, you're going to get a complete ticket. There's nowhere in between on the cost, because the cost won't be a problem. It's the tickets itself. So the tickets can't be cut in half. Either you get one ticket or you get no tickets. So because of that, that means that there's no partial ticket. So therefore, we couldn't use B. On this scenario, you would say that this is a discrete graph, and I would use a discrete graph to represent the following function. Okay, problem 3 was the last problem for this unit. Go ahead and finish up your summary and finish up your notes. Then we will see you guys tomorrow on this, and if you have any questions, bring them up. Okay, till then, bye.